Hi, I'm Dr. Montgomery. Let's go through the definitions of temperature, temperature scales, energy, phases, heat, and specific heat capacity. Let's start with temperature and temperature scales. Here on the left, we have a thermometer. It's measuring the temperature outside, how warm or cold it is. On the left, we see that we have a scale measuring in degrees Celsius. On the right, we have a scale measuring in degrees Fahrenheit. There is a third scale, one that is used in science, and it's called the Kelvin scale, or K for short. Notice that the Celsius scale has a degree symbol before the letter C. The Fahrenheit scale has a degree symbol before the letter F, but the Kelvin scale does not have a degree symbol before the letter K. Do not put the degree symbol before the letter K or say degree Kelvin. It's just Kelvin. The Celsius scale ranges from 0 degrees Celsius for the freezing point of water to 100 degrees Celsius for the boiling point of water. The Fahrenheit scale ranges from 32 degrees Fahrenheit for the freezing point of water to 12 degrees Fahrenheit for the boiling point of water. And the Kelvin scale ranges from 273 Kelvin for the freezing point of water to 373 Kelvin for the boiling point of water. 0 Kelvin is known as absolute zero. What do we mean by absolute zero? Well, to understand absolute zero, we need to understand temperature. Temperature is a number that corresponds to the warmth or coldness of an object, and temperature is measured by a thermometer. But what exactly is temperature? Temperature is a quantification of the speed of molecular particles in a gas, liquid, solid, or plasma. We could also say that temperature is a quantity that measures the kinetic energy of molecular particles in a gas, liquid, solid, or plasma. Gas, liquid, solid, or plasma are the 4 types of phases. For example, water can exist as ice, that would be a solid phase. It could exist as liquid as water. It could exist as a gas as water vapor. And a plasma is a higher temperature water vapor where the electrons are no longer attached to the atoms. Let's take a look at temperature and kinetic energy. We talk about the kinetic energy of molecular particles, and what we mean is the kinetic energy of translational kinetic energy. In other words, particles moving left and right or up and down. They're not spinning, they're not sliding past one another, they're just moving left and right or up and down. Translational kinetic energy. And remember that temperature is a measure of particles moving around. Let's take a look at 2 liters of boiling water. 2 liters of boiling water has twice as many molecular particles than the number of particles in 1 liter of boiling water. The total molecular energy in 2 liters of boiling water is twice the total molecular energy in 1 liter of boiling water. However, the average translational kinetic energy per particle is the same in the 2-liter container and the 1-liter container. The total molecular kinetic energies are different, but the average translational kinetic energy per particle is the same in both containers. Twice the kinetic energy in the 2-liter container has the same average as the kinetic energy in the 1-liter container. As average translational kinetic energy per particle is proportional to temperature T, the temperatures are the same for both pots of boiling water. So whenever we say the temperatures of a 2-liter or body of water and a 1-liter body of water are the same, we are saying that the average translational kinetic energy per particle is the same in both, not the total molecular kinetic energy. The total molecular kinetic energies are different in the two different pots. But the average translational kinetic energy per particle, in other words, the temperature, is the same. Let's look at translational kinetic energy in phases. Let's look at our phases. A gas phase is how fast gas particles bounce off of walls and each other. A liquid phase is how fast particles slide and jiggle past one another. A solid phase is how fast particles vibrate in place as molecules are connected. The pictures on the right are showing you a solid. The particles are all connected to one another, and because they're connected to one another, they can just move side by side or vibrate. The picture in the bottom right is showing you a liquid phase. The particles here can slide past one another. They can jiggle past one another instead of vibrating. And the picture in the upper right is showing you particles that are moving up, down, or left, right, and they're bouncing off of one another. Take a look at this animation of a gas, liquid, and solid. The gas has the particles bouncing around and bouncing off the container walls. Notice that the gas is moving up, down, or left, right, or at angles. The liquid has particles sliding past or jiggling past one another. And the best we can see with the solid is that the particles, since they're attached to one another, are just vibrating. Notice how fast the particles are moving in a gas compared to that in a liquid and compared to that in a solid. The solid seems to hardly be moving at all, whereas the liquid seems to be moving a little bit more, and the gas seems to be moving much more. Notice how fast the particles move in a gas compared to that in a liquid or a solid in the animation. The kinetic energy in gases is higher than that in liquids, and the kinetic energy in liquids is higher than that in solids. Heat is an internal energy transferred from one substance to another due to a temperature difference between objects. If two objects have the exact same temperature, then there will be no transfer of heat. Remember, heat is internal energy that is being transferred when you have two objects of different temperatures. The flow of internal energy, or the flow of heat, is always from a high temperature object or substance to a low temperature object or substance until thermal equilibrium is reached. In other words, they both reach a common temperature, the same temperature. The transfer of heat is only done so by three methods. They are conduction, convection, and radiation. These are known as heat transfer methods. Let's look at the quantity of heat. The quantity of heat is measured in units of joules, or J for short, or calorie, which is abbreviated CAL. There are 4.18 joules of heat required to increase the temperature of 1 gram of water by 1 degree Celsius. As such, we have a conversion. 4.18 joules is the equivalent of 1 calorie. Similarly, 1 calorie is equal to 4.18 joules. Let's look at the quantity of heat. Energy ratings of foods and fuels are determined from energy released when foods and fuels are burned. The unit of energy is called the calorie, or CAL for short, and is commonly used for foods. Heat unit for labeling food is known as a kilocalorie, or 1,000 calories, which is erroneously also called calorie for short. So even though you look on a package and it says calories, you're actually reading kilocalories. Heat is given the symbol Q. Heat added or removed is proportional to a change in the temperature of the substance. So if heat is added, you'll have a temperature increase. If heat is removed, you'll have a temperature decrease. Heat added or removed is also proportional to the mass of a substance. If you have twice as much mass, you need twice as much heat. Finally, let's look at specific heat capacity. Specific heat capacity is known as C sub SP for short. It is the quantity of heat required to change the temperature of a unit mass of the substance by 1 degree Celsius. It is a measure of how resistant a substance is to change in temperature. For example, water takes about twice as long to boil in an iron pot compared to a silver pot, as iron is more resistant to temperature change than silver. The specific heat of iron is 0.451 joules per gram degree Celsius, and the specific heat of silver is 0.237 joules per gram degree Celsius, which is about half that of iron. You can look up values for specific heat in tables in your physics text.